In this section, we look at absolute convergence and two new tests, the ratio and the root test, that will be related to this concept of absolute convergence. So let's first define what it means for a series to be absolutely convergent. So we say a series AN is called absolutely convergent if the series of absolute values, in other words, the same series but with the absolute value around each term, is convergent. So if the series of absolute values is convergent, we say that the original series is absolutely convergent. So let's demonstrate this with some simple examples. If I want to show that the series -1 to the n, or -1 to the n minus 1 over n squared is absolutely convergent, let's consider the series that we get when we take the absolute value of the terms. And in this case, when I take the absolute value of -1 to the n minus 1 over n squared, it just makes this alternating part become positive. So this is just simply the series 1 over n squared when we take the absolute value of the terms. Since this is a convergent p-series, we know that it's convergent. Therefore, it's absolutely convergent. What about this series here? We've got the series -1 to the n minus 1 over n, slightly different than the last example. When I take the absolute value of the terms of this series, again, it just removes the alternating part, so I just get the series 1 over n. And we know, of course, that this is the harmonic series, so we know it's divergent. So since we get a divergent series in absolute values, this one is not absolutely convergent. Okay. And one thing I should point out is that even though this one is not absolutely convergent, it actually does converge as an alternating series. So if I were to, for instance, now do the alternating series test with this, as we did in the previous section, you would see that it does converge as an alternating series. And actually, similarly here, this one also converges for the same reason. If I do the alternating series test, you would get this one converges, but perhaps what we'll see is that absolute convergence is actually a stronger condition than just normal convergence. So when we say that something is conditionally convergent, when a series is conditionally convergent, that means it's convergent but not absolutely convergent. Right? And we saw an example in the previous slide of exactly this, right, where we saw that the series -1 to the n minus 1 over n is convergent by the alternating series test, but because when I took the absolute values of it, we got a divergent series, we know that it's not absolutely convergent. So it's not absolutely convergent, and therefore it's conditionally convergent. And like I was saying, the absolute convergence of a series is a stronger condition than just normal convergence, which really means that if a series is absolutely convergent, then it implies that it's also convergent. So that's what we can say, is that if the series of absolute values converges, then the series without the absolute values must also converge. Right? Because if it's absolutely convergent, then it's normally convergent. Okay, but we should be careful. The other direction is actually not true. In other words, just normal convergence does not imply absolute convergence, and of course we saw a counterexample of that earlier, right? So if the series converges, the series of absolute values does not necessarily converge. It may or may not converge, right? That depends. So that's why here again we say that absolute convergence is a stronger type of convergence. So let's consider an example here. Determine whether the series of cosine n over n squared is convergent or divergent. So looking at it, notice that cosine of 1, cosine of 2, cosine of 3, and so on will not necessarily all be positive values. In fact, what we know is that cosine in general is between -1 and +1, but it's not always positive. So in this case, this is a series that does not have all positive terms. So in this case, if I wanted to, for instance, use a comparison test, I would not be able to with the series the way it's written, because the comparison test requires the series to have all positive terms. Okay. However, if we can create a new series that does have all positive terms, in other words, let's take the absolute value of the series. Now this series does have all positive terms. Now it's taking the absolute value of cosine. So now this series does have all positive terms, and therefore we can use comparison test. And now it's an easy comparison, because we know, like what we were saying earlier, that cosine of n has to be less than or equal to 1. So now we can say that the absolute value of cosine n over n squared has to be less than or equal to 1 over n squared. And we know that the series 1 over n squared is a convergent p-series. Therefore, by comparison test, the series of the absolute value of cosine n over n squared is also convergent by the comparison test. Now, what does this tell us about the original series? Well, since the absolute value of the terms of the series converges, we know that that implies that the original series must also converge. right? And so since absolute value of cosine n over n squared converges, in other words, the original series is absolutely convergent. Hence convergent.